Okay, let's begin. So this is an introduction to algebra for math competitions class, and I'm your instructor, Shreyas Shrivastava. And note, this is the last class since there was only 6 classes. So if you have any questions, please message me in the message box or email me at shreyasshrivastava@alphademic.org. After each topic, I'll present some questions to test your understanding, and then I'll discuss the solutions. For those who find the questions too easy, there will be some challenge questions. And most importantly, have fun. I'll try my best to make the class fun and understandable, but I'm not perfect. So if you see any mistakes, feel free to point them out. You can review the section at Alphademic's YouTube channel, and please consider subscribing to them as well. So the topics for this week are exponents and logarithms, some special functions, sequences and series, special manipulations, and then challenge questions. Note, this lesson was prepared with the help of the Introduction to Algebra book from AOPS. So Exponents. Exponents are basically the repeated multiplication of a number. The general form of an exponential function is f of x is equal to a to the power x. Because if you do like 2 times 2 times 2, and if you say, or you could write it as like a times a times a. So the general form is going to be a to the power x, or you multiply a x times. It's kind of how it is. And as the values of x are small, like as they're like pretty small, the function grows slowly. Because like if you look at 2 to the power x or something, right? So if like you have like small values, so 0, 1, it's going to go from 1 to 2, then it's going to go to 4, right? But as the x values become large, it's going to start going towards like 256, and then 512, and so on. So like it's going to start off slow, and then it's going to start rapidly increasing. That's kind of how the graph should look. Okay, so solving exponential equations. The best way to learn these are just to look at examples. So that's why I just put some examples. So the first question is, find x such that 3 to the power 2x is equal to 3 to the power x minus 5. Since you want them both to be equal, you can realize that the exponents have to be equal as well. Since if the exponents are not equal, then both of these won't be equal. So that means 2x has to be equal to x minus 5. That's it. So x is equal to negative 5. That's your answer. Pretty straightforward there. Okay, here's another example. So it says 2 to the power x is equal to 6. Find 2 to the power 3x minus 1. Okay, so what some people would do is like they like try to find x, which is going to be kind of annoying in this case because 6 is not a perfect power of 2. So the best way to do this is if you cube this essentially. If you cube this, it's going to be 2 to the power x times 2 to the power x times 2 to the power x times 2 to the power x. So it's going to look like this. That's your general thing. And we talked about previously how when you multiply exponents, it's essentially adding the powers. So it's just going to become 2 to the power 3x. So 2 to the power 3x is equal to 2 to the power x cubed, or is equal to 216. Now you want to find out what is 2 to the power 3x minus 1. So if you divide this by 2, then it's going to become 2 to the power 3x minus 1. So our answer is 108, because 216 divided by 2 is 108. Here's another example. So it says 4 to the power x minus 33 times 2 to the power x minus 1 plus 8 is equal to 0. Find x. So this is actually just a quadratic in disguise, because all you do is if you set 2 to the power x minus 1, wait, it should say like this. So it's kind of what I wanted to say. If you set this equal to a, right, and then this is going to become 4a squared, because a squared is 2 to the power 2x minus 2. which is just 4x minus 2. So yeah, so the quadratic simply just becomes 4a squared minus 33a plus a is equal to 0. And you want to find a. So if you factor this, you get 4a minus 1 times a minus 8 is equal to 0. So a is equal to 8 or a is equal to 1 over 4. If a is equal to 1 over 4, then x is equal to 4. No, is equal to negative 1. And if a is equal to 8, then x is equal to 4. Something important is a to the power b to the power c in this case, like kind of like this, is equal to a to the power bc, because you're multiplying a to the power b c times. So it's going to be a to the power b plus b c times. So it's a to the power b c. And a to the power b times a to the power c is a to the power b plus c. So I've seen many people confuse this. So it's pretty important to recognize the difference between both of these. So a to the power b times a to the power c is not a to the power bc. It's a to the power b plus c. Logs. Okay, so logs is kind of a different concept, but it's pretty similar to exponents. So logs are used when you want to find what power of some number is required to get some other number. So what I mean by this is, let's just say you want to find x such that 2 to the power x is equal to 64. You already know that this answer is 6, x is 6. But if you wanted to write it in a more neat manner, essentially, you could write it as x is equal to log 264. So what you're saying by this is 2 to the power x. Typically, it's written like this, not the x here. It's supposed to be here. So you're going to say 2 to the power x is equal to 64. So if you have log a, b, c, so like this, you are saying a to the power c is equal to b. Here's some examples using logs. So it says evaluate log 3 root 3 of 1 over 81. So you want to find out what 3 root 3 to the power what is 1 over 81. 3 root 3 is the same thing as 3 to the power 3 halves. You can figure that out pretty easily. And then 1 over 81 is the same thing as 3 to the power negative 4. So you want to find out 3 to the power 3 halves to the power what is equal to 3 to the power negative 4. So if you take a power, we talked about this, a to the power b to the power c is a to the power bc. So you want to find out what c is there such that 3 halves c is equal to negative 4. And this is pretty straightforward. It's just going to be negative 8 by 3. So another thing we can discuss is the domain and range of log functions. So like in this, let's just look at this example. It says y is equal to log 3x. You want to find out the domain and range. So you're just saying 3 to the power y is equal to x. And find all y and x that satisfy this. So clearly y can be any real number because there's no constraints on what the exponent essentially can be. So it's defined for all real y, but x has to be greater than 0 because 3 to the power y can never be negative. Okay, so here's another question. It says 3 is equal to k times 2 to the power r, and 15 is equal to k times 4 to the power r. Find r. You can divide both these equations, and it's going to become 2 to the power r is equal to 5. And this is simply just log 2/5. Log 2/5 is equal to r. That's all this is. Okay, here's some problems. I'll give you guys 2 minutes to work on them. Okay, let's discuss them. So the first problem says, find n such that log n 4 root 2 is equal to 10. Or you're trying to say n to the power 10 is equal to 4 root 2. Or you're trying to say n to the power 10 is equal to 2 to the power 2 to the power 5 by 2. So you're saying 2 to the power 5 by 2 is equal to n to the power 10. So if you can, you notice that since you're taking like essentially 4 times more, like n to the power 4 should be equal to 2. Because if n to the power 4 is equal to 2, then 2 to the power essentially 2.5 is equal to n to the power 10, which is true. So n to the power 4 is equal to 2, or n is equal to the 4th root of 2. Find x if log 9 of 2x minus 7 is equal to 3 halves. So 9 to the power 3 halves is equal to 2x minus 7. And 9, you can also say 3 squared to the power 3 halves. And that's clearly going to be 3 to the power 6. So 3 to the power 6 is equal to, 3 to the power 3, because you're taking the square root. I forgot that. So 3 to the power 3 is equal to 2x minus 7. So 34 is equal to 2x. So x is equal to 17. X is equal to 17. And the last problem was, find all x such that 2 to the power 2x minus 8 times 2 to the power x plus 12 is equal to 0. If we set 2 to the power x equal to a, we're going to get a squared minus a plus 12 is equal to 0. So you can factor this as a minus 6 times a minus 2 is equal to 0. So a is either equal to 6 or a is equal to 2. So let's take the easier case. If a is equal to 2, then you already know x is equal to 1. Pretty easy. And if a is equal to 6, so then you have 2 to the power x is equal to 6, or x is equal to log 2 6. So those are your two solutions. X equal to log 2 is 6, or x is equal to 1. Special functions. So I'm going to talk about some special functions which we did not talk about before. So one of them is the square root function, or y is equal to the square root of x, which is defined for all positive real x, because if it's negative, then you're going to get an imaginary answer, which you do not want. And notice that this is the inverse of y is equal to x squared. So here's an example. The square root of x squared plus 9 is equal to 2x minus 3. Find x. You square both sides. I went pretty fast here. So x squared plus 9, if you square both sides, is equal to, you can use a minus b whole squared, and you're going to get 4x squared minus 12x plus 9. Pretty easy right there. And then you can cancel these 9s. And then you're going to get 3x squared minus 12x is equal to 0, right? So one solution is x equal to 4, and the other is x is equal to 0. So that was the square root function. Then there's the absolute value function, which is gives you the value of how far away a number is from 0 on the number line. So what I mean by that is like this, you use this symbol to denote absolute value. So if you want to say like what's the absolute value of 6, right? So you're saying what's the distance from 0 on the number line for the number 6? Clearly that's going to be 6. But now if I take negative 6, this is where absolute value actually comes into play, where it's more useful. If it's -6, the distance from -6 to 0 is 6, because distance has to be positive. In general, the graph for the absolute value looks kind of like this. So if I have this is my grid, it's gonna go like this. That's my absolute function graph. Something important to notice is that y is never negative, because distance cannot be negative. So here's an example using absolute values. So it says find x such that 2x minus 5 is equal to 9. Find all x, I think I should have said. So first off, you look at when 2x minus 5 is positive. If 2x minus 5, the expression is positive, right? Then it's going to remain as 2x minus 5. So the value will be equal to 2x minus 5. So 2x minus 5 is equal to 9, or x is equal to 7. Now the other case we have to consider is if 2x minus 5 is negative, then the absolute value will make it positive. And to make it positive, like when we looked at -6, for example, when you take the absolute value of -6, and this is equal to 6, to make the negative value positive, you multiply by -1. So to make 2x minus 5 positive, you multiply by -1. So it's going to become 5 minus 2x. So 5 minus 2x is equal to 9. Or 2x is equal to -4, or x is equal to -2. So our answers are x is equal to 7 and x is equal to -2. Typically, when you see these type of absolute value questions, you have like 2 answers, but there's always some cases where you don't. Like here we had 2 answers. Okay, this is the floor and ceiling function. This one's pretty like different. You don't really see this one pop up as much on competitions, but you definitely see them a couple times. So if you want to take the floor function of a number, you simply use this symbol. So it's kind of like 2 L's and around the number. So the floor function, or the greatest integer function, denotes the greatest integer less than or equal to the number. So if you want to take the floor function of 3.2, that's equal to 3. So the way I think about the ceiling and floor functions is like, so you have a floor, right? This is your floor. Like think about any room or something. This is your floor, and then this is the ceiling. So this is your floor. Yeah, so this is your floor right here, and this is your ceiling, right? So if I have a number right here, let's just say I take some number here. This is my number. So the floor function is going to bring it down to the floor. So it's going to bring the value down, or it's going to take it down to 3. And then the ceiling function takes it up to the ceiling. So the number is going to go up, or go up to the integer that's greater than or equal to the number. So the ceiling function, you use like this symbol. So it's basically the floor function, but kind of like inverted, if you think about it. So the floor function of 3.2 is equal to 4. The floor function is also the smallest integer greater than or equal to the number. So in this case, which is 4. It's kind of how I think about it. If you forget, that's what you can use. So here's an example from Mandelbrot of this one's a floor function problem. So it says the floor function of the square root of the floor function of the square root of 345 is equal to what? And yeah, this was from Mandelbrot. So the square root, so you know that 18 squared is equal to 324. And you know 19 squared is equal to 361. So you know that this number, the square root of 345, is going to be 18 point something. Let's just say A, right? But that doesn't matter, because when you're taking the floor function, it's going to become 18. So this is going to become 18. And now you want to find out what's the square root of 18. What's the square root of 18? And you evaluate the floor function of that. So again, you know that the square root of 18 is probably going to be 4 point something, some A or B, something like that. But that doesn't matter, because when we're taking the floor function, the decimals get canceled out. So it's going to become 4. So our answer is 4. So that's how you use the floor function in a problem. Okay, rational functions. This is a function that is written as a ratio of two polynomials. So like it could be like 3x plus 1 over 2x plus 2. This is just an example. And to graph them, you have to look at the end bounds. I'm not going to go over them, but I think that's like an Algebra 2 concept. Oops. Okay. Partial fraction decomposition. To explain this concept, I'll just give this problem. So it says 2x over x squared minus 5x plus 6 is equal to a over x minus 3 plus b over x minus 2. So this strategy is essentially breaking down the fraction. So like you notice that x squared minus 5x plus 6 is x minus 3 times x minus 2. So the technique here is that we're splitting it into two fractions with denominators x minus 3 and x minus 2. So we want to find out a and b. So you know that a times x minus 2 plus b times x minus 3 is going to be equal to 2x. Or ax plus bx is equal to 2x. So a plus b is equal to 2. And then negative 2a minus 3b is going to be equal to 0 because there is no constant term next to the 2x. So negative 2a minus 3b is equal to 0. And then this one's equal to, what was it again? 2, yeah. So we can use our techniques of solving the system of equations. Multiply this by 2, you get 2a plus 2b is equal to 4. And then you sum both the equations, you're going to get b is equal to 4. Wait. No, wait. Negative b is equal to 4. That's what I meant to say. Is equal to 4. So b is equal to negative 4. So b is equal to negative 4. And then a is going to be equal to 6. So that's the partial fraction decomposition technique. Piecewise functions. Piecewise functions have multiple rules, or for some values of x, the expression for the function is different than at other values of x. I'll look at an example. Yeah, here's an example. So f of n is equal to n plus 3 if n is odd, and n by 2 if n is even. So you can notice that this function is different for different values of x, n in this case. Like if n is even, the function's down. The expression for the function is different. And if n is odd, the expression for the function is different. That's kind of what a piecewise is. So if n is equal to 2, what is f of n? So f of 2. So first, you evaluate f of 2. And since 2 is even, you do 2 divided by 2. So you're going to get 1. So you want to find out what is f of 1. And that's your answer. And f of 1, since 1 is odd, you just do 1 plus 3, or it's 4. So your answer is 4. Okay, here's some problems. I'll give you guys a minute to work on them because we don't have that much time left, and I have to discuss a lot. Okay, let's begin. So the first problem says find all x such that 4 over x minus 3 plus 1 is equal to 6 over x squared minus 6 plus 6. So we can do 4 over x minus 3 plus 1. And this is going to be equal to 1, right? Because x minus 3 plus 4 on the numerator, which is going to be 1 plus x over x minus 3. And this should be equal to x squared minus x. Oh, wait, sorry, 6 on the top. X squared minus x plus 6. Notice how x squared minus 6 plus 6 can be factored into x minus 3 times x minus 2. So if we cross multiply the x minus 3, this is going to cancel with this. If we cross multiply, so if you multiply both sides by x minus 3, so you're going to get 1 plus x is equal to 6 over x minus 2. So now it's pretty easy. You can cross multiply again. You're going to get x squared minus x minus 2 is equal to 6. Or x squared minus x minus 8 is equal to 0. Okay, let me continue. So now you can use the quadratic formula to solve this. Minus b plus or minus the square root of b squared, or 1, minus 4ac. But since there's a negative here, it's going to become plus 4ac in this case. So plus 32 all over 2a, which will be 2. So 1 plus or minus the square root of 33 divided by 2. That's your answer. Okay, find all r such that the floor function of r plus r is equal to 12.2. So there's two cases for r. First of all, r is integer, right? So r is simply just equal to a. No decimal, right? If there's no decimal, then the floor function of r is going to be equal to a, and then plus r, which will be a as well. Then 2a is equal to 12.2, or a is equal to 6.1. But that's not possible since a is an integer. So the other case we have is that a has a decimal point, like is a floating number essentially. So you can write that as a plus 1 over b, right? Because a plus some decimal, like when you have like 12.26, let's just say take that as a decimal, you do 12 plus 0.26, which is just 26 over 100. So you could express it like that. So that's why I'm expressing r as a plus 1 over b. That's a pretty important technique to use when you're solving these type questions. So if you write it as a plus 1 over b, the floor function of that will be a, and you're adding a plus 1 over b to that. This should be equal to 12.2. So clearly 1 over b will be less than 1, right? So that means that 2a has to be equal to 12. So a is equal to 6. And then 1 over b has to be equal to 0.2. And that means b must be equal to 5. So that's our answer. 6 plus 1 over 5 is equal to r, or 6.2. That's our only answer. Okay, find the domain of the function 2 plus 5x over 3 minus x. This is pretty straightforward. Clearly, any real x will work. Any real x will satisfy this function, except when x is equal to 3. The reason x is equal to 3 doesn't work is because the denominator becomes 0 and the function will be in an indeterminate form. So our answer is all real numbers except for 3. Okay, arithmetic sequences. Yeah, so this part of the lesson right now is going to be pretty crucial because this stuff definitely pops up a lot. So an arithmetic sequence is a sequence of numbers such that the difference between two consecutive terms is constant throughout the series. So let's look at some examples. So one example is 1, 2, 3, 4, 5, 6. Notice how 2 minus 1 is equal to 3 minus 2 is equal to 4 minus 3 is equal to 5 minus 4 is equal to 6 minus 5. They're all equal to 1. And this is also another arithmetic series because 4 minus 2 is equal to 6 minus 4 is equal to 8 minus 6, which is equal to 10 minus 8. You could say the same thing about this series as well. So something to note is that if the common difference is d, and by the common difference, I mean the difference between two consecutive terms, and the first term is a, then the nth term will be a plus n minus 1 times d. The reason this is true is because if the first term's a, then this is a plus d, right? And then a plus 2d. So you can notice that the third term has 2 as the coefficient, the second term has 1 as the coefficient, so the nth term will have n minus 1 as the coefficient of d. Okay, so that was arithmetic sequences. So here's some examples. Given the arithmetic sequence -9, -5, -1, 3, 7, find the three terms. So the key word to look at here is arithmetic sequence. That means every two terms has a common difference between them. To find the common difference, we can take any two terms, consecutive terms, and subtract them. So let's just look at like 3 and -1, just some random terms. 3 minus -1 is 4. So our common difference is positive 4. So our next three terms will be 7 plus 4, which is 11, 11 plus 4, which is 15, and then 15 plus 4, which is 19. Here's another example. Given the arithmetic series 4, a, b, c, d, 18, find a, b, c, d. If the first term is a, right? So we talked about this before. If the first term is a and the common difference is d, the sixth term, well, nth term, anything like that, the sixth term will be a plus 5d, right? So in this case, we have 4 plus 5d. Since the first term is 4, is equal to 18. So now you can find out d. D is going to be 2.8. And now you can easily find out a, b, c, d. It's just going to be 4 plus 2.8, which is just 6.8, plus 2.4, which is 9.2, and then 11.6, and then, yeah, you can just go on from there. Sorry, I meant 8.6. Right. Arithmetic series. Pretty much the same thing as sequences, but series are a long list of terms. So we take the arithmetic series with n terms, a plus d plus a plus 2d, all the way to a plus n minus 1 times d. And you want to find the sum of this arithmetic series. You can essentially just write this sequence backwards. So what I mean by that is, if you have the series a plus d all the way to a plus n minus 1d, you write the sequence backwards, which is like a plus n minus 1d plus a at the end. So the reason I did this is because if you do that, right, if you sum these two together, n minus 1, if you sum both of these series together, you're going to get 2a plus n minus 1 times d. Every two terms will sum to that. A plus 2, n minus 1 times d is this as well. So is this term going to be. So now you can easily find out the sum of the series because both of the sequences have the same exact sum. So if you divide the total sum by 2, that's our answer. So it's every term sums to 2a plus n minus 1 times d, and you have n of these terms. So if you divide that by 2, that's going to be your sum. So the sum of any n terms, the sum of the n terms in an arithmetic series is n times 2a plus n minus 1 times d over 2. You don't need to memorize that. You can just like remember the technique to quickly derive it. So here's an example. Find the sum of the first 100 positive integers. So many of you guys probably already know this is the formula, but I'll just show you how they got it. So we could use our previous findings to, right? So it was 2a plus n minus 1 d times n all over 2. So a is your first integer or number, which in this case will be 1. So this becomes 2. 2 plus n minus 1 times d, right? And there's 100 terms. Well, let's just say there's n terms. I'm trying to generalize here. If there's n terms, then this remains n minus 1. And then the d is 1 because it's positive integers and they're all consecutive. So this is 1. And then times n. So it's going to be 2 plus n minus 1 times n all over 2, which will be n plus 1 times n divided by 2. So that's where this formula comes from. Gauss derived this, I think. Yeah, Gauss did. So the formula is n times n plus 1 over 2 is the sum of the first n consecutive integers, n consecutive positive integers. So if you want to find the sum of the first 100 positive integers, you just do 100 times 101 by 2 divided by 2, or 5050. This is a formula you should definitely remember, n times n plus 1 over 2. Because again, it's not that hard to memorize this one. So here's another question using that. Find all n such that 1 plus 2 plus 3 all the way to 6n is divides 6n. Sorry. 1 plus 2 all the way to plus n divides 6n. So we can use our new formula we just found, and we can say 6n divided by n times n plus 1 divided by 2 should be an integer. Or 12n divided by n times n plus 1 should be an integer. And clearly these n's can cancel, so it'll be 12 over n plus 1 is an integer. So the possible n's will be n is equal to 1, comma 2, comma 3, comma 5, comma 11. Those are all your choices. So some people will say that n is equal to 0 works because 12 divided by 1 is an integer, but it's actually not going to work because 6n is going to be equal to 0, and then this sum won't, it'll just be 0. Let's just say that. And then, so 0 divided by 0 doesn't exist. Another interesting sum. So you are asked to find the sum of the first n positive integers, or 1 plus 3 plus 5 plus 7 all the way to 2n minus 1. You can reverse the series again. So you write it as 2n minus 1 plus 2n minus 3. You're going to get 2n plus 2n plus 2n n times. So it's going to be 2n times 2n times n divided by 2, or that's n squared. So this is also pretty interesting. The sum of the first n positive integers is just n squared. So geometric sequences and series. A geometric series is a series of numbers such that there's a common ratio between every two consecutive terms. So 2, 4, 8, 16, because 4 divided by 2 is equal to 2, 8 divided by 4 is equal to 2, 16 divided by 8 is equal to 2. Same thing can be said about this. If the first term is a and the common ratio is r, then the nth term will be a times r to the power n minus 1. This can easily be found as well. If you look at the terms a, 8r times ar squared, ar cubed, we find that for every group of 3 consecutive terms, the middle term is the square root of the other 2 terms, or the geometric mean of the other 2 terms. So what I mean by this is let's just look at these 3. So a times a r squared is equal to a squared r squared. And if you take the square root of a squared r squared, you get ar, which is the middle term. This is also said as the geometric mean, or the geometric mean of 2 numbers. Let's just say 3 and let's just say 12. So if you want to take the geometric mean of 2 numbers, you multiply them. So 3 times 12, and you take the square root, which is going to be equal to 6. Solving geometric series. If you have a series like 1 plus 2 plus 8 plus 16 plus 2048, and you want to find the sum, so if you want to sum them, then what will you do? So you let the sum equal s, and you multiply the series by 2. Or you're going to get 2 plus 4 plus 8 plus 16 plus 32 all the way to 4096 is equal to 2s. Subtract both of them, all the terms will cancel, except for this 4096 and the negative 1 that's going to be here. So you're going to get 4095 is equal to s. You can use a similar technique to generalize that the sum of the n terms in a geometric series, with the first term being a and a common ratio r, is a times 1 minus r to the power n over 1 minus r. This is also a pretty important relationship to remember. Infinite geometric sums. So if you have an infinite geometric sum, you can use similar techniques to show that the sum will be a over 1 minus r. So for example, if you want to find 1 plus half plus 1/4 plus 1/8, you can plug it into the equation as a is equal to 1 and the common ratio is half. So 1 over half, which is equal to 2. So this infinite sum is just 2. Something important to note is that for this formula to work, the ratio has to be less than 1. The reason that the ratio has to be less than 1 is because if it's like 1 comma 2 comma 4 comma 8, the sum is going to start to diverge, or it's going to go towards like infinity, which would be impossible to sum. So that's why you have to have a ratio less than 1. Okay, so here's an example using, you can use your infinite geometric sums to find these. So what fraction does 0.12727272727 forever equal? So, or you could write this as 1.127 with a line over the 27 because it repeats. This can also be written as 1 over 10 plus 2 over 100 plus 7 over 1000 plus 2 over 10,000, so on. So 1 over 10 has no infinite series, so you can leave it be. And as for 2 over 100 plus 2 over 10,000, so on, this is an infinite series with a is equal to 2 over 100 and r is equal to 1 over 100. So the sum, you can use the formula a over 1 minus r. You're going to get 2 over 99. And then for this one, 7 over 1000 plus 7 over 100,000, same thing. Use the common ratios in the first term. You're going to get 7 over 990. Sum these fractions, you're going to get 7 over 55. Or 1 over 10 plus 2 over 99 plus 7 over 990. Okay, telescoping series look hard, but in reality, they telescope down to a really easy expression to solve. So here's some examples. Okay, we're running out of time, so I'm going to try to go fast here. So 1000 minus 998 plus 998 minus 996, so on, all the way to 334 minus 332. Notice how these terms cancel. So do these terms. So will these terms, so on. This term will cancel, but this term will not cancel because there's no plus 332 anywhere. And so same thing with 1000. There's no negative 1000 anywhere, so it won't cancel. So your answer is just 668. Here's another one, 3 over 1 times 4 over 2 times 5 over 3 all the way to 40 over 38. So you notice that the last two numerators won't cancel because the denominators only will go up to 38. So 39 and 40 won't cancel. But then the 1 and 2 also won't cancel because there's no numerators of 1 or 2. So it's just going to be 40 times 39 divided by 2, or 780. Okay, this is a pretty important telescoping series to look at, so I won't rush it. So it says 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus all the way to 1 over 99 over 100 is equal to what? So notice if I write it as 1 over n plus 1, n times n plus 1, that's kind of what this is. This is equal to 1 over n minus 1 over n plus 1. You can try this yourselves to see that this is true. So all the sum just becomes 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3, so on. So then it just becomes 99 over 100 after you just cancel out all the terms. Okay, I'm just going to solve them right away because we don't have time. Okay, express 0.72727272 as a fraction. This is 7 over 10 plus 2 over 100 plus 7 over 1,000, and so on. You can use your infinite sum techniques. You're going to end up getting 72 over 99. Yeah, there's a technique you can use. If you see like 0.72 like this, or any number A, B, C, and it's being repeated, then your answer is just the decimal, so ABC in this case, over 9, like 999 in this case. So it depends on how many numbers are being repeated. So since there's 3 digits being repeated, it's 999. If it's 2 digits, it's going to be over 99. But notice this technique only works if all the digits are being repeated. It can be like 0.1, 2, 3, and the 2, 3 is only getting repeated. So it's just 72 over 99, or which is just 8 over 11. Again, you can use the infinite sum technique to solve this as well, but this is pretty fast. Okay, an infinite geometric series has a common ratio -½ and a sum 45. Find the first term. A over 1 minus -½ is equal to 45. A over 3/2 is equal to 45. Or 2/3 A is equal to 45. Or 135 by 2 is equal to A. So we're done, which is just going to be 67.5. Okay. Find the sum of the first 50 positive integers. We can just use our formula we found. 50 times 51 divided by 2, or 25 times 51, right? And then you can do your multiplication, find that out. Just 51 times 25, easy. Okay. Special manipulations. They're nasty looking problems, but some simple techniques can be applied and make the question rather trivial. Okay. So here's an example. There are two examples you can mainly look at. One is this one. This is a popular one to see, especially in math counts. So like x plus 1 over x is equal to 2. Find x squared plus 1 over x squared. So it looks like you don't have enough information. What do you actually do? Like if you square x plus 1 over x, you're going to get x squared plus 1 over x squared plus 2ab, right? And 2ab is just going to be x times 1 over x times 2, which is plus 2. This should be equal to 4. So you have your answer. X squared plus 1 over x squared is equal to 2. As for this question, simplify the square root of 6 plus root 11 plus the square root of 6 minus root 11. Let this sum equal x. Like let this whole entire expression equal x. Then if you square the expression, you're going to get x squared is equal to 6 plus root 11 plus 6 minus root 11 plus 2 root 25. Because you have to do the plus 2ab thing. You can find that out. So you're just going to get x squared is equal to 12 plus 10, because square root of 25 is 5. And this is 6 plus 6, so 12. So your x is going to be equal to root 22. And it's going to be the positive one. Don't take the negative one in that case. Okay, self-similarity. This is when you're given expressions that go on forever. So like 1 plus 1 plus 1 plus 1 plus 1 plus 1 forever. Obviously, that cannot be summed, but there are some that can be summed. Here's one. Here's two of them. These are the two major ones you'll see. So like you're asked, find 1 plus 6 over 1 plus 6 plus 1 plus 6 over, and it goes on forever. So you're like, oh, how will I sum this, right? So if you let this all equal x, this whole expression equal x, then what you notice is that this is 1 plus 6 over x is equal to x. Since this goes on forever, if this whole entire expression is equal to x, right? And this goes on forever, so since this goes on forever, 1 plus 6 over this thing, since it's infinite, that you notice that this expression is essentially the same as this. It's 1 plus 6 over this, 1 plus 6 over this, 1 plus 6 over this. So you have 1 plus 6 over x is equal to x. So now It's pretty straightforward. You can find that x is equal to 3. You can just plug it in and find out, or you can do quadratics, your choice. So here's another one. Find the square root of 20 minus square root of 20 like this. So this is it, and it goes on forever. So this also seems impossible, but if you let this equal x, right, and you square the whole entire expression, you get x squared is equal to 20 minus x. Because we let this whole entire expression equal x. Squaring it won't really change it because it goes on forever. So x squared is equal to 20 minus x. And clearly this is positive, so just find the positive root of this, and that's going to be equal to 4. Okay, here's some problems. Again, I'm just going to go over them now. A plus 2 over a is equal to 6. Find a squared plus 4 over a squared. You can square the whole entire expression. You're going to get a squared plus 4 over a squared plus 2ab, which in this case will be 4, is equal to 36. So our answer is right there. A squared plus 4 over a squared is going to be equal to 32. Easy. This type problem will definitely show up on math counts if you're doing it. So you better be careful for those. This type problem also shows up on math counts a lot. It was something what we talked about. It's similar to what we talked about before. It just has minuses. So let this equal x. Let this equal x. Square the whole entire expression. You're going to get x squared is equal to 12 minus x. Because again, this goes on forever. Squaring it once won't really make a difference. So that's why x squared is equal to 12 minus x. And you can solve for the positive root, or you could just look at it and figure out x is equal to 3. Pretty easy. Remember, for these type expressions, your answer is always going to be positive, mainly because of the square root, which has a positive root. You cannot take the negative answer. Do not do that. A cubed minus b cubed is equal to 120, and a minus b is equal to 3. Find ab. You can factor this because a cubed minus b cubed is a minus b times a squared plus ab plus b squared. So if this is equal to 3, then this is going to be equal to 40, because this whole entire thing equals 120. So since this is 3, this is equal to 40. Now a minus b whole squared, right, is going to be equal to 9. Or a squared minus 2ab plus b squared is equal to 9. And you know this is equal to 40. So subtract both these equations, and you're going to get 31 is equal to 3ab. And you're done. ab is equal to 31 over 3. Okay. Since I've already won pretty late, I'm just going to do the challenge questions. Okay. Suppose a and b are the roots of 11x squared minus 4x minus 2 is equal to 0. Find 1 plus a squared plus a cubed plus a to the fourth, so on, times 1 plus b squared plus b cubed, so on, forever. So simply just looking at this, you notice that the ratio is constant, right? Times a times a times a times a times b times b times b. And since it goes on forever, this should ring a bell that this is definitely an infinite geometric sum. So, and you also know that the a is probably less than 1, because there's no way they're going to make you sum it if it diverges or a is greater than 1. So 1 over 1 minus a times 1 over 1 minus b is equal to the roots of this. So you could find the roots and just plug them in. What I'm just going to do is I'm going to multiply it out, and it's going to become 1 minus a minus b plus ab. Now, I talked about Vietta's formulas a long time ago, but what Vietta's formulas say is the sum of the roots is negative b by a, and the product of the roots is c by a. And the product of the roots is ab, so that's just going to be negative 2 11. And you want to find out the negative, like -1 times the sum of the roots. And the sum of the roots is 4 over 11. So -1 times that is -4 over 11. So -4 over 11 minus 2 over 11, right? And then plus 1 is equal to 5 over 11. And then you could do 1 over all that, and that's going to be 11 over 5. So that's our answer, 11 over 5. It all came down to just knowing some easy tricks of the geometric sums and then Vietas. And this problem was pretty easy. Okay, if the areas of three sides of a rectangular box are 24, 32, and 36, what's the volume of the box? Okay, so this is not too hard, but the reason I put this is because I've seen problems like this pop up a lot as well. So let the dimensions of the rectangular box. Wait, first let me just explain what a rectangular box is, because this is not geometry. So I'm assuming you don't know geometry. Okay, so this is a rectangular box. It has 3 dimensions, A, B, and C. Okay, so the area of one face is AC. The area of the bottom face is going to be AB. And the area of this face is BC. Those are the 3 rectangular box faces that you can take the area of. So you know this is equal to 24. It doesn't really matter the order. It's equal to 32, and this is equal to 36. So you want to find out what is the volume of the box. You multiply all of them together. So AC times AB times BC. That's going to be A squared, B squared, C squared is equal to 24 times 32 times 36. Or 6 squared times 8 times 4 times 8 times 3. Times 3. Or you can say 6 squared times 8 squared times 2 squared times 3. So you want to find out the volume of the box. A volume of a rectangular box is ABC. So you just take the square root of this. You're going to get 6 times 8 times 2 times root 3. That's your answer. So this is just going to be 96. Yeah, 96 root 3. So like it looks like it's geometry, but that was just algebra. You just had to know some basic stuff about the volume of a rectangular box is ABC. That's it. Okay, last problem. Find the minimum value of x plus 3 plus x minus, sorry, the absolute value of x plus 3 plus the absolute value of x minus 7, where x is a real number. So notice that for you want this to be minimum, right? So for this, the absolute value being minimum, you want both of these expressions to be 0. That's not possible, but like you want it to be as near as possible to 0. So that means that x should be very close to -3 for this to be 0. And for this to be 0, it has to be very close to 7, right? So to fix that, what you do is you want to make it so that there's like a middle ground essentially. So it's like equally close for both of them. And for that to happen, you want it to be somewhere between -3 and like 7, somewhere between there. And that's where your number is going to be. So if it's between -3 and 7, then that means that this expression becomes, stays x plus 3 because it's going to be positive. And since x is going to be less than 7, this expression is going to be negative. So it's going to be 7 minus x. So we're basically done. The answer is just 10. Okay, thanks for watching. Those are some good weeks, 6 weeks of classes, but I think you guys should be pretty good in algebra now for the math competition especially. So thank you for coming to the classes, especially the people that came to all 6 classes. Thanks a lot. Yeah, so bye. I might host another class later on, but I'll have to see about that. Okay, bye.